Good morning again, and welcome to today's webinar, Photoelectric Solutions for Error Proofing. My name is Lisa Shaw, and I'll be your moderator. I work on the marketing team here at SICK, and I'll be hosting today's session. And I'm very excited to introduce today's speaker, Jim Gilbert. Jim is going to go in depth on how the WTT4SL can enhance your error proofing applications. Before we get started, I want to share that a recording of this webinar will be shared with you following today's presentation. Also, feel free to ask questions at any time during today's webinar by typing your questions into the Q&A section on the right-hand side of your screen. One last thing I'd like to mention is if you do have any audio issues, please try calling in using a cell phone rather than using your computer for audio. We have found in past webinars that this is a great workaround. Now I want to turn our time over to our presenter, Jim, a market product manager for SICK. I want to introduce him really quickly and share that he has over 25 years of experience in industrial automation, and he continues to have a deep curiosity about finding solutions for problems faced by end users and machine builders. Also, some fun facts about Jim is he and his family live in Minnesota, enjoy biking, camping, cross-country skiing, and any activities near the lake. Jim, that sounds like a great way to spend time outside. I'll turn it to you.
Great. Thanks a lot, Lisa. Appreciate it. We just had the dusting of snow today in Minnesota, so looking forward to getting outside when we can. Today, we are going to look at air proofing, and one of the highlights we're going to look at today is SICK's new sensor called the WTT4S. It's a time-of-flight sensor in a very small body style. But before we get into that, I want to share a few different applications which we found very critical, and depending on what sensor you select, it can really influence the behavior of the application and the success of the process. So with that said, I'm going to look at a couple applications to different types of sensors. One is a background suppression sensor, and we'll contrast that against a time-of-flight sensor that uses a different technology to detect objects. So first off, we'll take a look at the diffuse sensor of the proximity or triangulation style, also known as background suppression. So triangulation sensors evaluate the energy coming back from the object in addition to the position of the spot on the receiver. So inside of the sensor, there is a small receiver, and based on the actual location of where the received light hits, it can determine its position using triangulation. There's also some algorithms that are tied in, and they can suppress backgrounds such as reflections, or maybe there's shiny objects in the background, including, say, ambient lighting. It can also suppress those things as well. But that is really how you're able to resolve an object versus its background, is the difference between, it can really detect the difference between the object and the background, and that's how triangulation works. So in contrast, the time of flight, it actually is measuring the transit time of a beam of light between the emitter and the receiver. As I show in the picture down below, you're actually looking at the time it takes for that beam to travel from the sensor, hit a target, and then be received back. And with this technology, you're able to see longer range of targets at longer distances. You're also able to detect shiny target objects, even though they might say be at some angles that background suppression sensors could not detect, and objects that are presented at steep angles. It might be a cardboard box, or it could be a tire. These things are all able to be detected very well by time-of-flight sensors. So those are some differences. There are cost benefits going to a background suppression sensor. So, if that is more of a selection process, then you do want to be sensitive to that. But in some cases, a time-of-flight sensor can be more robust. We're going to go into some specific applications and help you understand when to choose which sensor, just simply based on its optical properties. So looking at this sensor I mentioned before, the WTT4S, is shown on the right-hand side. This is a very small sensor in the SICK family. We call it the W4 family. And what it offers is long sensing range, out to about 1.3 meters. Now, in the chart I show in the upper left-hand corner of the screen, I'm showing a dotted line, and that's really a breakpoint. Below 150 millimeters, you would be better off actually using its background suppression counterpart, which is known as the WTB4S. In that case, below 150 millimeters, you actually have better resolution. And so there's a domain where each sensor really has its sweet spot, and you want to be able to apply those sensors in the right applications and maximize their benefit to the application that you're selecting. So for longer ranges than say 150 millimeters, you'd probably end up going with the time of flight version. For something shorter, where you need maybe tighter resolution, then you'd be looking at the background suppression version of the sensor. So there are two different domains in which they work, and that table or that graph really kind of sets up the context of what we're talking about. And this would largely apply to other families of sensors as well. So from SICK's perspective, we have some features about the time of flight family of sensors that we have. One is that it's unmatched detection. It has sensing range that goes from 50 millimeters up to 4 meters, and we can get down to 1 millimeter resolution. That ability to detect objects at any angle, as I mentioned before, even like a black tire, you're able to see these at steep angles, and so that can be really helpful in a variety of applications. And then also increasingly, these products are this technology is getting placed inside of smaller and smaller body styles. So you're able to get the benefit of those solutions in increasingly small packages. So SICK and other suppliers of time-of-flight sensors have a broad range of offerings. This is a sampling of what SICK has in this offering. On the left-hand side, we see one family called the WTT12. And then over on the right-hand side, the third sensor over, we're seeing the WTT4 family. And then next to it is another little brother called the WTT2. So you can see there's many different SKUs and models available. They have sensing ranges that go all the way from 3.8 meters down to just under 1 meter at 0.8 meters for the WTT2. But then also you should take a look at the response time. So depending on your application, you may or may not need that response time. If it's a fixed application where there's not really any movement, it might be a assembly cell prior to the next process. In that case, maybe response time isn't that big of a consideration. However, if it's an object moving on a conveyor, or the object is free falling or something like that, then you may have to consider faster response time. So just something to keep in mind as you're going through selection. So we're going to look at a few different applications, and pretty soon I'll turn on my camera and we'll actually visually show these. But what we're trying to tease out of this is the properties of steep angle detection, edge detection, and slot or hole detection, which is really similar to edge detection, and then small object detection. So I'm going to start off with small object detection, and in a second I'll flip over to my camera. Before I do, I want to set the table with a few different applications that you could look at, and just to get your mind thinking of how you could solve these applications. So one is this being solved with this sensor called the WTT2. In this case, you have a work cell, and you need to sense the targets. And in this case, it could be upwards of 800 millimeters away, but it's a pick-and-place robot, and so it just simply needs to detect that this transport unit is in the right location before beginning a process. So this sensor is really good at when it first sees a target. So as that target is presented, it does have some hysteresis, so it would say lock onto that target if it was then going away. But when you first are able to detect it, it does a really good job. Because of its compact size, it's like literally about the size of your thumbnail, it easily fits onto end effectors of many sizes. So its compact size and its long sensing range can really help out in a variety of applications. This is an example of a WTT4. I have a small video that is showing it picking up the box as well. On the left-hand side, we show something in the SICK logistics facility in Germany. So this is a larger gripper, I guess what I'd say is picking up totes, but here we've embedded the WTT4 right into that gripper, and it's able to detect, is there a tote there before it picks it up. in the image that you're seeing on the right-hand side, we've mounted the WTT4 onto an end effector of a universal robot. And with the vacuum suction, it's able to pick up a box. And basically, we're using the sensor as kind of collision avoidance. If someone were to sneak in an extra box where it shouldn't be, the robot would be able to detect that and not have a collision. So here's a few different applications. This is from automotive assembly. So in the upper left-hand corner, we're looking at steep angle detection. Again, this might be in a robotic work cell. So the operator might bring a part, might manually bring a part into this workstation. They position it into a certain location. They may use sensors to verify that its position is in the right spot. And then also the lasers, the sensors may be used to verify that, say, parts, maybe there's a PEM nut or some other piece of hardware that needs to get mounted. And then the robot, it'll get pushed into place, and then the robot takes it from there. It might go through a welding process, or it might move on. As you can see in the upper right-hand corner of that image, eventually this part becomes part of a complete assembly that goes into a car. So you can see that in this case, the object may be presented at a steep angle, and that's important to be able to see it from a healthy distance because you want to be outside of the operator's work zone and still see the object at a steep angle. In the image on the upper right, we're looking to verify that the hole is there. If you look in the back of your trunk or something of your car, you'll notice sometimes there are these knockouts that are there. Oftentimes they serve a purpose, and they have the same thing with in metal parts of your car as well. So if those holes aren't there, as that piece advanced through the assembly process, then they won't be able to, say, pull through a wiring harness or put on a fastener. So it's really important that those holes are verified before it moves on to the next assembly. So it might be 4 or 5 steps down the line where that hole is finally used. So in this case, I'm showing 2 examples. One is called the WTT12L Shiny Precision, and then also another is this WTT4SL. And both of these would do a good job for detecting holes up to 1 meter away. Next part, on the other end of the scale, for looking at very small and short distances, we have a sensor called the WT12, is a background suppression sensor. There's a PowerProx version of that also that is called Precision Shiny. So in this case, I say have like a cylinder and you're looking for the ring around that cylinder. This could verify it has a very small light spot and could resolve a very small object and make sure that that part is in place before you advance to the next workpiece. For handling assembly applications, here again, you need to be mounted some distance away from the work cell. In this case, we're actually looking at assembly of a sensor. So you can use your sensors to inspect assembly of your sensors. You could use something like a W12 distance if you have to have tighter resolution. Then we could look at what I was talking about before about the WT12 laser, or then also the Precision Shiny version. And then finally, in the right-hand side, we're just looking at another work cell before, say, ultrasonic welding process is done. Just want to verify that those parts are in place before you advance. So moving beyond that, think of other applications outside of automotive or outside of metalworking. You can imagine that you need to verify that eggs are in a box or a carton. Make sure the cartons get counted and placed on the pallets. So here you could be looking just to verify, do I have all my cartons or boxes arranged properly before they advance and get palletized? So there's just tons of applications. Today we're highlighting some automotive applications specifically. So with that said, we're going to take a look at a few different actual applications, and we're going to tease out why these sensors can be used in these different applications. So what I'm going to do now is I'm going to turn off my screen, and I will turn on my camera and allow you to see me. But I think I need to stop sharing here so that you can see my screen full size. So okay, and I do have a camera here. You should be able to see the objects that I have on this surface. And the first application that I'm going to take a look at is I have mounted a, I'm going to call it a PEM nut or a nut. I've mounted a nut onto a piece of aluminum. So imagine this was going into a work cell and it needed to be welded in place by a robot assembly. So in this case, switch over to a different power supply. In this case, what I'm going to do is the name of the game here is to see the nut and not the background that it sits on. So what I'm going to do is position the sensor so the laser is on my target, and I'm going to teach it. I'm going to teach it to the PEM nut. So be careful, this is kind of a caffeine test for me, see how much caffeine I've had today. But if I can do it right, I can teach it on the nut and not detect the background. So do that again in case the cable was in the way. But, so basically I'm detecting the nut and not the background. So as I was showing before in those applications in the slideshow, this would be a really critical process because maybe a robotic welder is going to come in and weld this into place. And then it'll advance on into another part of the process. So that's a good example. Another sensor that would be good at resolving that. Here I'm at a distance of maybe 200 millimeters. Another sensor that would be good at that is the background suppression version. So these both can resolve over very small differences between the target and the background over relatively short distances. Say maybe upwards of 600 up to millimeters, maybe up to a meter. So this particular one is really good. You could do something, say, like resolve the thickness of a business card laying on a table. And so that's something that if you had a more precise application, then it would probably lean towards this type of a product, similar to the image that we had shown before with that pissing ring. So another property of these sensors, oftentimes it's not determining if a product is on another surface, but looking at a product, looking at a surface and trying to resolve it, detect it at a steep angle. So what I'm going to do in this case is I'm going to teach it on this this is a black matte card, basically what I have. So the light doesn't bounce off this card very well. And I positioned it so it's on this, essentially it's a protractor, and so I'm going to rotate it through an angle. And so just take a look at the lights on the camera, you'll be able to see if it's actually, when it actually turns off. Just to verify where the switching point is, I'll pull the target back, and then I'll stop pushing it in until the light comes on. So there we are. So now I'm going to pivot about this axis. So as I'm rotating it, just look at the output lights on the sensor, and you'll see how long this can stay on. So right now I'm at 45 degrees. You have a very stable output on the sensor. I'm going to keep rotating. I'll stop as I get further along. Now I'm at about 70 degrees, very stable output. And then now I'm at like 85 degrees. Now I'm down here at 90. So in our tests that we've done before, we've been able to take a target like this and look at it like upwards of almost 89 degrees. So it's at really steep angles. Now, if you move to something that has a shiny surface, that can be more difficult. So in this case, I'm going to use the same teach point that I had before, except now I have an aluminum surface. This is a paint scraper I got from the hardware store. And as I rotate this, you'll see that it won't be able to resolve quite as far. So as I'm rotating it, I'm looking for when it turns, and I'm looking at my detection angle, and that is a detection angle of maybe close to 25 degrees. So you can see the big difference between a matte black surface and something that is shiny. There is a big difference. Now, we've got different sensors within our portfolio. I had mentioned before in those images that we have a W12 distance laser, and this can actually go to a steeper angle. And we'll get into some reasons why in a minute. But if I swap this sensor out and put it in place, I'll do a quick check to see how far it can, see what angle it can detect at. So So I will swap over sensors real quick. And I'll do the same teaching process. So I won't do it on black. I know that'll be a very steep angle. So now we'll take a look here. Teach it on the surface at about, again, about 200 millimeters. We'll just verify that switching point by bringing the target in again. Now I will begin to rotate. You can see if you're not right on, you could already get some challenges just because this thing is fairly shiny. I'm teaching again. Now I'll begin to rotate. Well, I think what's going on is I have this, got two angles going on right here. There we go. Well, so much for live TV, but I would be able to, done properly, this sensor would be able to get a slightly steeper angle, and we'll get into the reasons why in the next example. So in the next example, we're going to take a look at this is a drill gauge that you might find at the hardware store. So in this case, what I'm going to try to do is to slide the drill gauge in front of the sensor and detect the holes. So you can see what I've done is without even teaching it, I'm able to see these holes and I'm able to get down pretty small. This is a 5/16 hole that I'm able to see through and without any issues. So I'm going to set up this card. I have my laser. I'm going to try to position it right at the midpoint of these holes. And what I'll do is I will teach a surface directly behind the card. So I'm going to take a look at the more robust surface. This black box. So I'm teaching to this black box, and then I'll place the card in front. So I've just taught at this distance, and then what I'm going to do is slide my card right in front. Again, I'm at about the diameter of these circles. I'm going to pull away this black box. This is just a reference so I can know where to teach the sensor. And as I slide it through, you see that I'm having a little bit of problem now detecting. But if I bring in this background again, it can change its behavior. So the point is that depending on how far away the background is, that can change the behavior of the sensor. And so for your application, it can be really important whether you have a background or not. And we're going to take a look at another sensor, going to move into the one we had mentioned before. This is the WTT4S. So this sensor is very small, very compact. And we're going to use the same drill gauge, except now I'm going to try to teach the sensor on the target directly behind one of these holes. In this case, I'm going to use this black card. So I'm going to press down on the teach button on the top. And now I'll pull away the card. Let me pull the card out real quick. There we go. So I have a teach point. Now what I'll do is I'll slide my target in front. try a different target here. There we go. So what I'm able to see is that I'm able to see up to a 3/8 inch hole at this distance. And as I move across, I'll be able to see all the holes just because they're larger. So what I'll show you is that if I do this right, I should actually be able to see smaller holes, but it's going to depend on how far away is the background. So in this case, I'm just going to use my hand. And what we found is that the distance to the background can really determine how small the hole you can see. So the important thing here is that when you're selecting your sensor, you need to know all the parameters here. So despite the challenges that I had with the setup, what I would recommend for small hole detection would be this WTT4SL, and then also this WTT12 precision shiny laser. So these would be really good at both hole detection, but the same thing would be true for edge detection. So let's say that the application was not sensing a hole, but it was sensing when the laser or the sensor first sees a target as it slides into place. Both of these sensors would be very good for that. However, if you needed to see something at a steep angle, then what I would recommend is this product called the WTT12 distance sensor. So this would be better and more forgiving for seeing objects at steep angles. So that's kind of an overview of what the family is. I apologize about some of the setup challenges I had, but I'd be happy to take any questions that folks have.
Thank you, Jim. Yes, if you have any questions, please type them into the Q&A section on the right-hand side of your screen. Jim, one question you could start off with is, you've highlighted some examples for the automotive and handling and assembly. What are some examples?
Yeah, for other industries, you know, I showed a picture of, say, case packing or, you know, primary and secondary packaging is a really big place where maybe you want to make sure that, say, a flap detection. You want to make sure that a flap has been folded over properly before, I'll just use my camera while I got it here, to make sure that a flap has been folded down before it advances on to case packing. So that would be a simple application for packaging. In the next step, you might want to verify that you have all your boxes in place before a gripper comes down to pick them up and place them onto a pallet. So as you progress through to finally, when you ship your product, there's many different locations where you might find that. Another example you could imagine, like this is one, I don't know if they actually use this type of sensor for detection, but say like in a juice box, you want to verify, is the straw there? Is the straw in place on the box? You don't want to have your juice boxes go out without the straws. So anyway, those are a few different applications that might lend itself to airproofing in packaging.
Great. Another question from attendee is, can the push buttons on the sensors be locked out so the operator cannot adjust them?
That's a good question. We get that a fair amount of time. The push buttons, some of our sensors do have IO-Link built inside, and you can see the IO-Link symbol. So in that case, you can use IO-Link or set up through the PLC to essentially deactivate the manual button. So in a lot of cases, OEM will build a machine and they want to keep it set up that way so it's locked out. That would be one way that you could do it. As an end user, you may have the ability with a key or some sort of a password protection to override that, so if manual setup was required. In a lot of cases, increasingly, customers are doing remote teaching of their product. If you did need to do a manual teach, you could override that and do it yourself as well. So good question regarding the lockout.
Cool. This question comes from Paul, and he asks, what is the max distance on these sensors?
So the max distance on the sensors, I think what I'll do is I'll go back to my, my PowerPoint slide. Try to share here again, Lisa. So I'll just index back up here. So looking at, it's about the 1, 2, 3, 4, fifth column down, I've highlighted a few of them, but for our WTT12 distance, it goes out to 3.8 meters. For our precision shiny, it does 1.4 meters. So there is a pretty healthy range going from 3.8 down to 0.8. So it really depends on your application as far as which sensor you're going to select. But if you're just trying to see an object at 3.8 meters and you didn't need to resolve millimeters, that WTT12 distance could definitely see out to 3.8.
Great. Those are all the questions we have currently. Anything else you'd like to add, Jim, before we wrap this up?
No, I guess what I'd say is that reach out to your local SICK salesperson or their regional market application engineer. They're very well versed at the entire SICK portfolio, but specifically with these sensors for airproofing applications, this is something that we have a lot of experience in, and we can help with the selection process. So there's obviously a lot of different sensors available from SICK, and we can help fine-tune your selection, whether it's something on the very small size or maybe something, if you can afford a larger package size, you might be able to get more performance from that sensor as well. So thank you for your time. And again, please reach out to your regional salesperson if you have additional questions. You can also call SICK Tech Help as well for specific applications.
Thanks, Jim. And yes, to our listeners, please visit SICK.com to know the latest about our products and also about our upcoming webinars and trainings. Thanks again, Jim, and have a great day.
Great. Thanks, Lisa.